Okay, so let's go ahead and finish up some of these problems. So the idea here is we're looking always for a perfect square. We were just talking about what the perfect squares are. So for example, some people did 8 times 6 is 84, or is 48, sorry. And that is true. Neither one of those are perfect squares. So if you continue to break down 8, you have 4 times 2. Well, that's a perfect square right there, right? 6 is 2 times 3. And the thing is that 2 times 2 is another 4, right? So I could essentially write 48 as 4 times, if I want to do 2 times 2, that's another perfect square, but I can go 4 times 4, because that 2 times 2 is another 4, times 3. Now the definition of a perfect square is a number times itself. So anytime you see a number double, that is a perfect square, right? 4 times 4 is 16. So this could also, you could also have started with 16 times the square root of 3, right? What's the square root of 16? 4. So here you would have 4 square roots of 3. Let's do 500. If you look at the list of perfect squares, you might see a number that goes evenly into 500, but if you don't see a perfect square right away, then you can always factor the number. So I was talking about using the prime factorization. 500, I saw some people had 50 times 10, right? And then here, okay, here's 2 times 25. 2 times 5. Well, we're looking for a number. Here's 5 times 5. We're looking for any doubles. So these are all prime. The prime factorization of 500 is 2 times 2. There's 2 2's. And 5 times 5 times 5. Anybody that's doubled is a perfect square, right? Because that's 4 and that's 25. So 4 times 25, those are both perfect squares, times an extra 5. This extra 5 is not a perfect square, so it has to stay locked inside the radical. The only people who get passes to come out are the perfect squares, right? And maybe it's helpful to write that as the square root of 4 times the square root of 25 times the square root of 5. So 4 becomes 2, square root of 25 becomes 5, and this radical 5 has to stay. It cannot come out because it's not a perfect square. So does everybody see how I'm getting this process here? Yes, you can do it in more than one way. If you're not seeing the perfect square right away, 5 times 100 works too, because notice if you get 2 times 5 here, this gives you 10 radical 5. You probably got the exact same answer. But when you see, if you look at 500 and you go, oh, I want 100 to come out, 100 is the perfect square. Yeah. Okay, while we're here, let's just do this last one here. Negative square root of 12. What did you break this one down to? 4 times 3. And so that would be square root of 4 times the square root of 3. I'm just writing it like that again so you can separate it out. But essentially, the reason why we get a 2 on the outside is because we're taking that square root of 4 gives us the 2. Square root of 3 is not a perfect square. Any more questions about that? Yes? Yes. Uh-huh. Yep, the 3 stays in because it's not a perfect square, but since we can take the square root of 4, and it's essentially similar to factoring, right? I mean, we're looking for factors of the number that are a perfect square. So if we do the entire prime factorization, we start to see those perfect squares are there's always 2 of those factors, Okay. Let's just go on to the next thing here. Yes, Which one are you talking about? C. So 2 times 2 is 4, but we're talking about the square root of 4, right? What number times itself is 4? 2. Yeah. So only 1, 2 comes out because we're just going back to the idea of like, what is the square root asking us? Square root of 4 is saying what number times itself is 4, and that number is 2. Yeah. Okay, so only when the number is a perfect square. So let's look at these. Use the multiplication and division properties of square roots. Multiply and or divide the following and then simplify each. So what's happening here is that we can multiply inside the radical. So we're essentially going to multiply the whole numbers out front, 4 times 5, and then the square root of 3 times the square root of 7. These numbers are not 3 and 7, right? They're much smaller than that. So we can multiply them under the same, under the same radical. That's that division property that we saw before. X times the square root of y equals the square root of x times y. So here we have 5 times 4 is 20. What's the square root of 3 times the square root of 7? 21. Now, when you look at the square root of 21, ask yourself, can you simplify it? What do you think? The answer is no, because the only two numbers that multiply to 21 in this example are going to be 3 and 7. Neither one of them are doubled, right? The prime factorization of 21 is 3 and 7. Neither one of those is a perfect square. So therefore, the square root of 21 cannot be simplified anymore. Okay, let's look at B over here. Any thoughts about what we would need to do here? Yeah, multiply the 12 and 6 since they're both under the radical. So we have 5 times the square root. And instead of writing, now I could multiply them together. Okay, yeah, actually, let's multiply them. What's 6 times 12? 72, right? But in order to multiply 6 times 12, do you notice that when you look at 12, it's 6 times 2? Yeah, do you see that? So this is the same thing as 5 times, I could have written, instead of multiplying them, I could have written it as 6 times 2, and then I'm going to multiply it by another 6. So that's the same thing as 36 times 2, right? So what can be simplified? The reason why I'm writing it out as factors like this is so that you can see that I have 2 6s. If I have 2 of them, one of them can come out, right? The square root, because that's a perfect square. 5 times 6 times radical 2 is 30 radical 2. Are you seeing that? How I'm doing that? You're following? Okay, here, if you multiply 10 times 2, are there going to be any numbers that double? Yeah, because 10 is the same thing as 5 times 2. I'm going to be multiplying by another 2 because of that second radical. I mean, that would be the same thing as 2 radical 20, but what I want you to see is that 4 is a factor of 20. That's the perfect square right there. So what will this become? 2, another 2 comes out, and 5 stays in, right? So we have 4 radical 5. Was there a question? I thought. Yes? B? So this is the idea that what is the square root of 36? 6, right? Only 1 6, because the square root asks the question, what number times itself? So really, when we have the square root of 6 times 6, that answer is 6. There's only one of them because it's saying what number was times it by itself. Okay, good questions. What about D here? So what do you think I should multiply? 10 and 3, so that gives me 30. And then 6 times 8 is 48. So really this 30 is just out here. It's minding its own business. It's already out of the radical. So 30 times the square root. Tell me, like, how will we break down 48? Into 12 and 4 you want? Okay, so if we do 48 is 12 times 4, is there another perfect square in 12? What are the factors of 12? 4 times 3. So 48 is the same thing as 4 times 4 times 3, which is really the same thing. Maybe it would be easier if I wrote it this way. 16 times 3. You see the 16 is the perfect square. Yes? You could do that too. You can do this really however it gets you there the easiest way, right? So you could multiply them and then factor them, or you could factor each one of those as well. So 16 is the perfect square, right? The reason why I wrote it here as 16 instead of 4 times 4 is just so that we see that we're taking the square root of 16. So we get 30 times, what number is going to come out? 4. And then why does the 3 have to stay inside? It's not a perfect square, right? So now we have 30 times 4 is 120 times radical 3. That's the answer here. Okay. What about this one when we multiplying fractions? 5 6 times 1 6. What's that going to be? 536. Square root of 5 over the square root of 36, just because I didn't write my radical big enough, but that's the same property. That's the division property, right? Is either one of these a perfect square? Yes, so the 5 stays in. The square root of 36 is equal to 6. So here I'm going to multiply 2/5 times 3/20. Now when I multiply fractions, can I cross cancel? Why not, right? 2 goes in here once, 2 goes in here 10 times. Can you cross cancel with 3 and 5? No. So this becomes the square root of 3 over, anyone? 50, which is the same thing. I'm going to move over here and I'll change colors so that it stands out. It's the same thing of square root of 3 over square root of 50. Oh, it's not 30, sorry, 3. Can the square root of 50 be broken down any further? Is there a perfect square inside of 50? What is it? 25 times 2. So this is equal to the square root of 3 over the square root of 25 times 2. Square root of 3 over, how does the square root of 25 times 2 simplify? 5 radical 2. Okay, here are some problems for you to try.